Hello everyone, this is Erwin from Carnegie Mellon University and Tokyo Institute of Technology. Today I'm going to introduce a new hand pose interface for wearable devices. Before we start, I want to acknowledge the collaborators from all over the world. We have Ye and Professor Kitani from CMU, Hui-Shyong from University of St. Andrews, Professor Quigley from University of New South Wales, and Professor Koike from Tokyo Tech as well. This work cannot come true without any one of you. Thank you. Okay, as we may know, human's hand is the most common tool for us to interact with other objects. Nowadays, we use our hand to operate touchscreens for smart devices. We're using gesture to control the TV or home appliance. Also, in the field of mixed reality, hand interaction is one of the most natural ways to control a virtual avatar. However, the current hand pose detectors still have a lot of limitations. Hand-mounted displays or some gloves can detect the hand pose precisely, but will disturb the user due to the extra and bulky equipment. On the other hand, some wearable cameras are used to track the hand, but most of these cameras are placed at a weird place to observe a hand, which can be only used in limited conditions. While most natural way might be a third-person view cameras, which don't need to have disturbing devices on human's body. However, these cameras are mostly fixed and therefore cannot be used in the wild. Some recent works also try to solve this problem. Chang et al. Introduced the Cyclops ring, which used a ring-like fisheye camera placed between the fingers to observe the hand and to classify the hand gesture. Chen et al. Introduced a elevated camera to observe the dorsal hand from above to recognize the finger angle. However, these two setups are still hardly to be called a natural way to detect the hand pose. Okay, before we proceed, I have a question for you. We could see that most previous work estimate the hand by tracking the fingers. But do we really need to see the fingers? I want you to raise your hand like this and observe the back of it carefully. Next, try to tap your finger periodically. Do you see your skin, your bone, your vessels is moving together with your fingers? Yes, that's exactly what we want to use in this paper. We want to extract the deformation of the back of the hand and estimate the 3D hand pose using a single RGB camera. There are a few smartwatches in the market which have a side camera for photography. We believe this technology could be applied on these wearable devices. In our previous work, published in last year UIST, we built a prototype which used a depth camera to classify the gesture from the back of the hand. This time we want to further this work to a full hand pose tracking from a single RGB camera. Here you can see the overview of our approach. We use a wide-angle RGB camera on the wrist, of which image is shown in the middle here, and we calculate the motion history from the hand pose and pass these two information to our network. Finally, we regress the 3D hand pose from the image. Let's take a glance at our hardware. As mentioned before, in this paper we employ a 120-degree fisheye lens camera for prototyping. Because the current field of view of a normal camera on a watch is not enough to see the whole hand, as we saw in the previous video. However, we fixed the cameras at the same height as a real watch, so we do believe that this camera could be easily embedded into a wristband device in the future. Before we input the image into a network, we perform some real-time processing to reduce the noise and extract more features. First, we use an encoder detonator network to remove the background and get a mask hand image. Next, the motion history image is calculated from the past 5 frames to extract more motion features. This video here shows the real-time result of the image preprocessing. First, you can see the hand masking. We can tell that it is also robust to different lighting conditions. Next, these are the motion image tapping different fingers. You can realize that different part of the back is changing when tapping different fingers. Okay, finally, we have the major contribution of this paper, the DorsalNet. We use a two-stream CNN network, of which each stream is a simple ResNet 18. to extract the information from the hand image and the motion image. After that, the network is followed by an LSTM layer for temporal feature learning. To enhance the temporal feature, we use a LSTM-based Kalman filter network instead of a normal LSTM. A bypass is also added to the network to choose whether to use Kalman filter or not. Finally, the network outputs a 19-dimensional finger representation and is recovered to 3D hand pose by an inverse kinematic-based hand simulator. Hereby, we use a special 19-dimension hand representation, of which the first 16 values stand for the joint angle for each finger. The DIP and PIP have only one value, while the MCP has two, a vertical rotation and a horizontal rotation. And the sum is represented by a 3D vector independently, because it is quite difficult to see the change of a sum from a whisk camera. Therefore, we want to ease the work of the network to simply estimate a sum vector and leave the rest to the hand IK. Good, let's take a look at the real-time result of this work. To show the effect of our system, we perform several studies for evaluations. First of all, we collect data from several users, and the setting is shown in the left figure. The ground truth data is collected by the leap motion IR camera. Finally, we collect the data from 5 users, of which each user did 15 gestures, including 10 static gestures of American Sign Language number and 5 dynamic gestures of each finger tapping. All gestures are recorded 30 seconds for 5 sessions, which results in 225 frames in total. For the evaluation, we first study the accuracy of our system on each finger and joint. The MAE stands for the mean absolute error of fngers, while the SD is the standard deviation. By comparing all the fingers, the ring finger achieves the lowest error, while the index and middle finger doesn't fall much behind. The accuracy of pinky finger as well as the thumb is worse, because the deformation related to these fingers could be hardly observed from the dorsal hand. On the other hand, for each joint, the vertical MCP performs the best. However, the horizontal MCP rotation has a quite large error, which was out of our expectation. Next, we compared our network with other baselines such as the nearest neighbor, a simple direct regression, and other state-of-the-art networks, where our network performs better both with and without Kalman filter. In order to show the robustness of the network, we also run the test in 5 different lighting conditions: outdoor daytime, outdoor nighttime, and indoor dark condition, together with the baseline indoor condition. The outdoor condition with sunlight cannot be quantitatively evaluated because the leap motion IR camera cannot work under strong sunlight. But we already saw the real-time results from previous video. In the restful conditions, the average error increased in dark condition with bad lighting, but there wasn't a huge difference between the best and the worst lighting, which was within 1 degree. We also run an ablation study on different network architecture and inputs. starting from simple direct CNN to two-stream ResNet. By comparing the first two architecture, we can see that the ResNet has a similar error with a much faster inference time with VGG. Next, comparing the 3 to 5 lines with different inputs, it indicates the motion input has a greater effect on accuracy than the RGB only condition. And of course, the two-stream input has the best accuracy. Lastly, the 3 lines indicates that the Kalman filter and our data augmentation has effect on improving the accuracy. Besides the gesture recognition, we also noticed that when your hand is grabbing some items, the dorsal hand is also quite different, which depends on your grasp type. So we also evaluated our system on grasp recognition. The right figure shows the confusion matrix of 50 tests for each gesture. In classifying 11 grasp types, our system achieved a 75% overall accuracy, while the worst cases appears in T1F, T2F, T3F, which is the picking motion of the thumb with another finger. To show the usability as well as the potential of this research, we developed several types of applications. Well, let's summarize today's contents. First, we proposed the DorsalNet to reconstruct angle-based 3D hand poses from image of the back of the hand. Next, we studied the accuracy of the 3D hand pose estimation by comparing with several baselines and an ablation study. We also evaluated the system on gesture and grasp recognition to show the potential. Finally, we showed several types of real-time application using our system. Last but not least, we still have some improvements to do for this work. Currently, we just perform a simple wrist angle estimation by the center of the backhand, and cannot deal with the roll of the forearm. In the future, we are going to build a full hand pose estimation system by also including the movement of the background. Also, the system now works in a dim dark environment, but since it is using an RGB camera, it still will not work in a completely dark environment, which need to be improved. Another problem is the number of subjects. Due to the corona pandemics, we only collected 5 subjects from the university. More variations in hand shape as well as skin color is required to prove the robustness of the network. And last, of course, we want to implement this system on real watches. That's all for the presentation. Feel free to contact me if you have any question about our paper. Thank you.